in section 2.8, and this is on differentiability. All right, differentiability of a function. All right, differentiability of a function. We're basically, up until now, we said, does a limit exist? And we looked at the function. We determined if a limit exists. We determined whether or not the function was continuous. Now we're looking whether or not a function is differentiable at a point. All right, so that's what we're looking at. Is a function differentiable at a point? So I'll start with this function. There we go. That's some polynomial, everyone. This is just, I do want to point out it's a nice, smooth polynomial. But where is this function differentiable? The answer is everywhere. So this polynomial here, you don't even need the equation. You can look at the image. This is the x-axis, that's the y-axis. But this polynomial is differentiable everywhere. Everywhere. And so you go, what do you mean by differentiable? The derivative of f exists everywhere. That's what I mean. And we did two-sided limits. That's f of x. We did two-sided limits. Well, now you're thinking about like how the slope from the left equals the slope from the right at every point. Now I can just pick a point like right there. Is the slope as it approaches from the left side matching the slope as it approaches from the right side right there? Yeah. Are the slopes equal coming from the left and from the right? Because slope of a tangent line to a curve is a derivative. I'll say it again, that's what a derivative is. It's the slope of a tangent line to a curve.
One goes up and the other one comes down.
Then it's no good. Very good. So that's what we're going to focus on. I like how you think. That's easy. It's nice, everyone. It's nice and smooth everywhere. So that goes for all polynomials. They're going to be differentiable everywhere. So we got to focus on when are they not differentiable. And you figured out one thing. You said if you had something like this, something came up like this and something went like that, right? Ooh, thanks. Yeah, you could just put it right there. Thanks for doing that. She had about 3 hours of traffic. Ooh, yeah. Hey, so you nailed it. So that's what we're going to focus on now. And all right, all polynomials, I guess they're going to be differentiable everywhere. Let's focus on where is the function not differentiable. Then we'll be good. So where are functions not differentiable? And you go, what's differentiable mean? The derivative exists at the point. You go, what's a derivative? So we got to get all these words down. Derivative, we're talking about the slope of a tangent line to the curve. And so again, just before I erase this, like even at that point right there, does everyone agree? Like the slope from that side matches the slope from that side right at that point. Yeah? And that'll exist everywhere in this group. So we go right to it. All right. Differentiable function. Where is a function not differentiable? Or when? I should change where to when. Talk about the different occurrences. When is a function not differentiable? All right. I'm going to start out with yours. You did something like, they came up like this, and then they came up like that. Oh, those slopes are not equal at that point. So it wouldn't be differentiable at that point. So we're going to start out with C, corners. C for corners. You got a corner in a graph. You nailed it. And if you got a graph, you got something like this, like a little corner, like a V somewhere. Yeah, at that point right there, at any corner, at that location right there, let's say there's an x value for this dot, the function is not differentiable at that point. Do you all agree? We go, why? Because does the slope from the left of that dot match the slope from the right? No. So very good. I'm going to put another word for C.
Is there a way to do that?
Let me finish this up, and then I'll get your question. I like this with corners, but let's also put cusps. And I'm going to show you what a cusp is. A cusp looks like this. It's not really a V, but it might come up like this, and then it comes up like that from that side. Now, can you see this is really, really steep and positive, but this is really, really steep and negative? And so that's another one. Oh, go ahead.
Is there a way to prove it mathematically?
Absolutely. Yeah. It's just looking at, remember, he does math proof. So what you have to do is, remember the derivative definition? I'm going to write it down. What's the definition of a derivative? It equals the limit as h approaches 0 of f of x plus h minus f of x all over h. And you'd have to do this from either side. So you'd have to do like a plus or minus here. So remember that from the left side and the right side? So I'm going to write this another way. Here's another way to look at f prime of x. You can say f prime of s is the limit as x approaches a of f of x minus f of a all over x minus a. Remember we were talking about how this, I'll hide this. Remember this was the secant slope? And we add that and you get the slope of a tangent. So you would do this, but then you do a left side and a right side. And that's your mathematical proof. So that was a good question, because could you do it, man? Like, how do you do this in an elegant way? Mathematics is interesting, like with notation. You'd have to do all that work, but you'd have to do a negative for the left side, then a positive right side, and make sure those slopes what match. Very good. Hey, so when C, corners, cuts, I got two more letters for you. The next one is V. V for vertical tangents. V for vertical tangents. All right. What do we mean by vertical tangents? I'm going to give you an example of a function. So here's my example for vertical tangents. It'd be something that did this. The graph went up like this. And then it looped over like this. It actually changes concavity. Does anybody know that word concavity? This is like, it went from concave up, and then the concave down. But everyone, right there at that one instant, if you think about the slope of a tangent line here, but right there, the slope of a tangent line to that curve would be totally vertical. What's the slope of a line like that? It's undefined, yeah. And so that's why we're saying, oh, then the slope would be undefined. And that's why we're saying that's another place where a function is not differentiable. You go right here at this location at an instant, and we look at the slope of this line. The slope would be totally vertical, and it's undefined. So V for vertical tangents. I do want to point out sometimes if you're just given an image, it's hard to tell. So don't worry about that. If you're unable to, you might be like, I can't tell if it's really a vertical tangent, and maybe it's just really steep. And I understand that. Got one more letter, J. I don't know, does JVC still make equipment, like electronic equipment? Oh, good. So that's what I use. I like this acronym, JVC. Acronyms help us remember things, you know, like mnemonic devices, JVCs. Where is a function not differentiable? JVC, V for vertical tangent, C for the corner cusp that you hit on. J stands for jump discontinuities. Jumps and discontinuities. J for jump, or jumps. Well, I can give you some examples of those, everyone. What's a jump discontinuity? Something like this. Oh, the graph went like this, stopped here, started here. Yeah. That's one example of a jump discontinuity. See how it jumped? Right? Basically, I'm talking discontinuity where it's not continuous. Here's another one. And when this is a jump discontinuity, hole, and it continues like that, but there's a hole there. So I'm talking about right at this location. The function is not differentiable here. Right here, the function is not differentiable. Cool? Right there, there just can't be any one. Jumps. So the acronym JVC, J for jump discontinuities, V for vertical tangents, C for corners and cusps, and we're able to identify exactly where functions are not differentiable. He went on to the algorithm. He said, what about math proof? If you wanted to really prove it, you could go and dive into the function I give you and show this from the left and right side. Cool. So in my next exercise, I'm going to draw a graph. I'll put some numbers down. I was wondering if you could identify all the x values where the function is not differentiable. Good news, you'll see practice problems that I chose in the textbook on this. But I'm just going to draw a picture. I'll go left or right. I guess I can do it over here. Can I do it right here? Would it hit it? Was it too far away? Awesome, I'll do it right here. And we can leave that up. All right, here's my graph. All right, this graph does this. Let's see, it comes down like this. Let me put a bunch of x values down. Okay, that's good. 1, 2, 3, 4, 5, 6, 7 is the x-axis. -1, -2, -3, -4, -5, -6, -7, -8, -9. We're going to make sure these line up though. Because I know you all are already identifying where this function is not differentiable. I'll just call this f of x. I mean, this does pass the vertical line test, right everyone? Make sure that's just, I'll just put an arrow there. Maybe I can make this look a little bit better. I want that to be smooth. I'm trying to make the thing come up. There we go. That'll work. That will work. At this location right there, let me make sure that lines up. That's it. X equal to -5. Right there. All right, let's see if we can do this. So where is this function not differentiable? Not differentiable. Question mark. Just list the x values. As you can tell, I didn't put any y values down. Anybody got one? X equal to -5, right there. Boom. Corner or cusp, right? If you're looking, is that a corner or is it a cusp? It's one of those. And x equal to -5. I'll put a comma because there are more, right? What's another one? -2, another corner or cusp? Any more? 2, +2. And maybe that's it, but do you see one where perhaps it is? Where? 4. What's it look like that's going on at x equal to 4? Yeah, but see, again, it's like I'd have to make a really good sketch. I was trying to show that this thing got really, really what? Yep, totally vertical. Totally vertical here. So if I can improve that, make this look a little bit better. Make that smooth right there. So it does look like everyone at x equal to 4, there is a vertical tangent right here. So we can mark this thing up. Boom, right there. There's a vertical tangent. This was a jump, right? Jump discontinuity. This was a corner, this was a corner. Awesome. Everyone okay with that? Put a problem like this on the next test. Give you graphically. Yeah, no JVCs, right? What we're saying is the function is not differentiable at JVCs. Hey, you'll laugh. A student who graduated 10 years ago on Facebook wrote me a message, like within the last year, and he just, that was what he wrote. He's like, JVC, function not differentiable. It's like, that's what you remember? All that calculus. For some reason you remember this. I was cracking up. It's like, you remember that? Ah, I guess it works. I guess it works. Hey, we won't do a proof for this problem, but I do want you to think about, I'm going to put something on the board, I'm going to put a piecewise function, and I'm going to ask you about 3 things. Does the limit exist? Is the function continuous at the point? And is the function differentiable at the point? All right? Now, before I do that, I think we should put a phrase with the words differentiable, continuous, and limit. We should make a little diagram for that. So how about this? Washington, D.C. is lovely. Will that work? Washington, D.C. is lovely. That's not as cool as JVC. But DCL, what I'm saying is, if a function is differentiable at a point, that arrow means then. Then the function has to be what? Continuous at the point, which also implies that the function has to have the limit existing at the point. The only thing is, can you reverse this order? No, it wouldn't always be necessarily true, so make sure you don't reverse it. But if a function is differentiable, then it must be what? Yep, at that point. If a function is differentiable at a point, then the function must be continuous at the point. If a function is continuous at a point, then the limit, the two-sided limit, must exist at the point. The only thing is, you can't do this, right? Look, does C imply D always? No, not always. I'm going to put a slash to it. Can Emily give me an example of a function that's continuous, but it's not differentiable? Watch, someone will call it with one. Just show the counterexample of why we can't say C implies D.
Vertical tangent.
That's a good one. I love that. It says a vertical tangent. You know? He goes, hey, it's continuous here. That was a good one. It's continuous right there. That's nice and continuous, but it's not differentiable. Here's mine. How about the absolute value of x graph? Yeah, like that. That was a good one. How about the y equal absolute value of x graph? We all know it's a v, right? It's continuous right there, but it's not what? It's not differentiable there. So we can't say C implies D, right? But Washington, D.C. is lovely. D implies C implies what? L, always. So if that helps you in your logic, I think it's great. I do want to point out you can reverse these and do a contrapositive if you put the words not. For instance, that's not true, but you can say this in math. Not C does imply not D. You can do that. You can do that. It's called a contrapositive. You can reverse it and put nots. It's actually logic. You ever take a logic course? Oh yeah, there we go. It's logic. It's this idea of logic. You can reverse it and put nots on it. If a function is not continuous at a point, then it is not differentiable at a point. All right, here's my problem. See how you do with this. Can I erase this? Yeah? All right, JVCs, we got it. All right, differentiability of a function. Here it is. F of x equals, I got a piecewise, I made this up. All the other classes taking the quiz. Sitting here brainstorming something. 3x minus 1. If x is greater than or equal to 2, comma, if x is less than 2. Hey, you all are awesome coming out on this Thursday night, hustling through crazy traffic and all that. See? So, this problem won't be on the test Tuesday, but it will be one just like this on the final. So I'm going to give you that heads up. She made it all the way out here. Plus the people watching the video. They're the ones who got stuck and had to turn around and go back. No, but yeah, I'll put one. You'll see one of these on the final. It's a nice final type of question. Conceptual stuff. But all right. All right, what am I? There's a function. It's a piecewise function, right? That's a parabola. What's this? Aha, so you got parabola, straight line, but maybe it is differentiable when they meet. It'd have to be smooth, wouldn't it? Right? Yeah, the slope from the left would have to match the slope from the right. I mean, you could design a roller coaster like that, right? Something came out like this, parabola, and then you attach the nice straight line right here. As long as you hit the slope perfectly, you're good. True? So that's what we're looking at. So here's the question. You know, which statement is true? The limit as x approaches 2 of f of x exists. All right. Letter B. F is continuous at x equals 0. And letter C, f is differentiable. Differentiable means the function's derivative exists at x equals 2. And it can be more than one of these. All three of these could be true. Only one of these could be true. None of them could be true. We're just going to check them all out, right? Almost like a true-false. Which statement is true? Is this true or is it false? Is this true or is this false? Is this true or is it false? That's what we're going to check out. I'm going to start with limit. How do you check limit? How would you check limit? Yeah, we could do that. I was thinking this. Let's check continuity. Right? And if it's continuous there, then it has to have the what? Does that work? So when I say let's check continuity first. Now, do we have to make a graph? No, because he had an idea last class. I'll let yours. What do we simply have to do to check continuity?
Replace your 2 with that, or x for 2, and solve.
Check the
If we're even.
Love it. And you know what we're going to do for check continuity? Let's start there, because it's so easy. Plug a 2 in, plug a 2. They got to match. If they match, continuous at x equals 2. If those y values don't match, it's broken. It's not continuous.
What if it matches, but it's like it's not continuous, like in a linear math?
Well, if it matches, it's got to be continuous. If these two y values match,
Oh yeah, I'm talking.
right? As long as I use that same thing, but now you're under. You go, oh, it might not be differentiable. There you go. And we'll get to that. We'll do that afterwards. Very good. Very good. This is calculus, right? You got functions that are continuous, but sometimes they're not so differentiable there. Yeah, all right. All right, is it continuous here? Check. True. Very good. True, everyone. And we're going to show why. Look, in this case, what's 2 squared plus 1? 5. What's a 3 times 2 minus 1? 5. Y value is equal. These two y's are the same. So, what does letter A have to be? True. If the function's continuous at the point, then the function's got to have the limit exist in there, right? Yeah, it's connected, so of course the limit exists from both sides. I was just curious, we don't have to do a proof, but we do have to know how to get derivatives. Who knows the derivative of this graph? AKA, here's my hint, derivative means slope of tangent. Who knows the slope of a straight line? Slope of a straight line, mx plus b. I'm going to write that here. I'm hearing it. But I'm not, isn't that a straight line? mx plus b straight line. Which number is the slope? 3. Aha. So what's the slope from the left side? Right? The slope from the left side is a what? 3. True? All right, so I'm going to write this down. Slope from left at x equal to 2. I'm just putting words. You could do this if you wanted to. You'd have to put a little minus here, though. If you wanted to write the math notation, everyone, like a math, like a mathematician, you're like, I don't want to write words. You'd have to write all this and put a 2 here and then put a little in the minus here. But I'm talking about the slope from the left is the value what? 3. Sure? Now, how to get the slope from the right? I taught you this at the end of last class. Remember the power rule?
F prime.
Yeah. What's the slope? How to get the derivative? Do you remember what you can do? Instead of doing it the long way, move the 2 in front, and then we have to decrease the power by what? 1. So let me write that down. So that's slope from the right. I'm going to put a wall. What's the slope? Slope from the left. What's the slope from the right? We're saying it's the derivative. So I'm going to put that word down. You know we're doing a derivative from the right. Just like derivative from the left. Slope from the right. I'm going to use the power rule though. 2 in front. Decrease the power by what? 1. But And what's the derivative or slope of a constant?
0.
0. So this is it. But what number do I have to plug in here to see if it matches?
2.
Yep, it's always at that, right there at that value. So I'm going to put, everyone, would you just plug in x equals 2 into this expression? What's 2 times 2?
4.
Are the slopes matching? So what's the answer? What's going on with C? True or false? False. No. Is F differentiable? No. No for this guy. Slope is 3, slope is 4.
How come you took the derivative of x squared plus 1 but not derivative of the bottom one?
Oh, you could do it. Do you want to do it? Because I was thinking we could think algebra. Slope of a line is slope of a tangent line. It's just slope. Because remember, derivative means slope. It's easy with straight lines, isn't it? But if you want to do it, what's that power right there?
P3.
Oh, good. So it'd be 1 times 3 x to a 0. Now I'm going to write that. You get 1 times 3 is 3x to a 0. Well, what's x to the 0 math? 1. So very good. You can do it every time.
Can we just look at the continuous points and see whether it goes in the linear pattern or?
You could do that. Yeah, but the key is you really, whenever we're talking about that for differentiable, for it being differentiable or not, we really have to focus on that slope right at that point. We have to do the derivatives. Hey, try one more, everyone. This time, just do letter C, okay? Just do letter C. True or false? One more for your notes. There you go. No. I like this better. Try that one. Is F differentiable at 2? So I use 2 again. Remember, there's my cutoff 2. That's smooth everywhere except we're running about 2. By the way, if you notice something, everyone, I made sure it was already continuous. I want to point that out. I made sure it was already continuous. Can you tell? 2 squared plus 1 is what? 5. What's 4 times 2 minus 3? 5. I made sure it was continuous because D implies C equals L, but not C implies what? Not D. If it wasn't continuous, it's not differentiable. So I don't want to, I want to make sure I gave you something that was continuous. So this, everyone, this is already continuous at x equal to 2. I was just curious if you could figure out whether or not it's differentiable. Slope. Well, this is going to be the same slope, right? What's the slope from the left? 4. What's the slope? 4. What do you think? Parabola meet in straight line, but the slope is exactly what? 4 at that instant. From the left side, from the right side. A little from the left, from the right. I'm sure mathematicians love to just keep writing all that stuff, but I want you to focus on it. It's like, I just got to look at the slope, the derivatives.
Why is the slope for derivative from the right slope is 4? Because last time you did it, now you did it 2x and you multiplied it 2.
Oh, you're right. So that was the same thing here. Let me make sure. This was from the right side, right? I'm going to break all this. So this went with this. That's true. That stayed. That stayed the same. This now, this part came from here. But try it. What's that derivative of that function? Well, it's a straight line. So we know what the slope is. It's 4. But you can still do this rule, the power rule. There's a 1 right there. 1 times 4. Decrease it by 1. You get 4x to a 0. But x to the 0 is just what? 1. Or if you wanted to do that, but that's the long way, isn't it? Yeah, we're like, okay, we did that once. We get it. Cool? Awesome.
Is it differentiable then?
Yeah, I'm sorry, I never put the answer down. Yes. Let me get that out of the way. It's sitting on the video going, false. Oh, this is what? This is true. The answer is yes. Yes, it is. And what would this look like, everyone? You'd have a parabola that did what? What goes on it, too? It would hit here, it would hit here, and it would come up like this. So here's the picture. And then right at that point, 2, 5, you'd have it meet this what? This straight line, but it would be nice and what? Smooth. Boom. Smooth. Slope left, slope right, right there at that point. Right? It's like someone's designing a roller coaster that came down and what? Just went off in a straight line. Have you ever seen things like this? Or water slides like that. You know, the water slide comes down, that's like, but they make sure they don't give you the water slide like this, do they? And then it's like, true? Right. Right. I used to guard in Ocean City, everyone. But this is back in the day. I don't know if you were born in 1987. And they just built a slide on the boardwalk. So my guard stand was right off the boardwalk. And it was the first year of this thing. But there's not much room on the boardwalk, is there, for a water park? I don't know if this water park's still there. So they put a slide in. I am not lying to you. It was like super steep slide like this. The catch pool, I am not lying to you, was that long. Let me fill it in with water. I mean, you all, the first time I saw this, because I worked in a water park years before this, I'm like, oh man, are they asking for trouble? I mean, they're asking for lawsuits and stuff. I mean, this is what I saw. I mean, it was super steep and stuff. And everyone ever gone on a water slide, you get on your shoulder blades, you bounce like a rock. Yeah, so they're like, no, we'll put a sign up that tells them, that, oh, come on. Everyone, the manager there, he said people were losing teeth. Yes, loose teeth. I mean, they came in and just boom, right through the wall. They bounced up on the cement, cut all up and stuff like that. So they started, you're going to laugh at this, they kept it running, they were trying to keep a business going. So they'd have the attendants that worked there, they'd hold the raft at the end. They'd all stand with raft. I'm true story, I'd watch them, they just stand there, so you get paid, you know, like, back then we got paid like $4 an hour. I was like, $4 an hour, just stand with raft. This is true. I mean, you saw it come. It's just dealing with, you know, basic physics. It's like, yeah. You gonna let that go? All right. I want to be like Freeman and just keep talking about water slides, right? Hey, and the last thing we got to do, 2.8, is we're going to get a function of f, and we're going to graph the derivative of f. So now we're going to graph the derivatives. Graph the derivative. This is cool. So I'm going to give you a function f. You and I are going to get an idea what the graph of the derivative looks like. So let's see. This will be my first one. How about this guy? Graph it like this. Almost like one of those trig graphs, you know? How when this is almost going to look like one of the trigonometric graphs, like a sine or cosine, y equals sine of x, y equals cosine of x. Let's call this f of x. And then if you can in your notes, I think it helps. Would you, if you have room, right underneath it, let's graph f prime. Because it really helps us stay organized. So right underneath this, we're going to graph f prime. I'll put it in green. F prime of x. We're going to graph that. I'll just keep it nice and all right. We go x-axis, y-axis, x-axis, y-axis. I'm going to graph the derivative. This is fun. If you're curious, what I like to do in my exams, on these, I like to do a matching, and the textbook has a matching exercise. I put it for practice. It's one of your practice problems to try out, so it's good practice. See if you can get that one. But in this case, I'm going to graph the derivative. It's not hard. This is what I want you to do. Would you focus on this graph right now and tell me where the slope of the graph is 0? I'm talking like this. If you threw a tangent line to that graph, it would just be flat. Can you give me some spots? I want you to look. That's the first thing I want you to look for. You see one?
At the top of the...
Nice. It goes right at the top. So when I'm at boom, boom, right there, and I'm actually going to draw the slope of it, like slope 0, right? Now, what I want us to do, right away, come down here. Go straight down. And I want you to put a dot right there. You know why? Because derivative means slope. And what's the slope right there? 0. Do y'all follow me? I know a lot of you are copying. I'll wait till you're done copying, but that's what's going on here, really. Hey, your f prime is 0 here. F prime means derivative. It's 0. Slope is 0. F prime is 0, m is 0. M means f prime. F prime means derivative. And you go, what does this mean? This means slope of tangent drawn to f. Right? It's the slope of a tangent line drawn with a curve. So, okay, there's the slope of a tangent line at 0. If I'm graphing the slope, then it would be what right here? 0. So far, so good? Yeah. Any other spots? Let's do it. Right over here. Hit these first. Go down. Go down. Right here. There it is. Go straight down. Why is it right on this x-axis? Because the slope is 0 right here. F prime is 0. F prime equals 0. M equals 0 there, right? Now, to finish out a rough, we're just making a rough sketch of this graph, by the way. To finish this thing out, let's now look in between. In between these spots, because there's no more slope to 0, true? Right? Cool. Let's go over here. Would you just put a tangent on that thing and tell me if it's positive or it's negative? So I'm just going this curve. Just how about right here? Is that slope positive or negative?
Positive.
So I'm going to write f prime pos, and then I'm going to come down here. I won't even do the dotted lines anymore. I'll just come right here, and I'm going to put a dot up here somewhere. I'm just estimating. You go, where is it? Well, I'd have to know exactly that slope, right? I'd have to actually measure I'd have to measure the rise over the run there. But I know it's positive, right? So where are the positive values? Up here. Where are the negative values? Down here. So I'm just going to put a dot right here, like, how about right there? That work? Now, everyone, how about in between these two slope of 0? What's going on, like, right there? I'm going to put a tangent line arrow, and here we go. What's that slope?
Negative.
F prime is negative. So, I'll just come down here at this location, put a dot down here somewhere. Where do I put it? Well, I just know it's negative. I have to measure the rise over the run there. That's a bad looking tangent. We'll make that a little better. Tangent hits that thing in one spot. Get that. There we go. So that, negative. Hey, one more. How about over here? What's the slope right there? Slope's positive. Boop. And just put a dot right up here. The last thing, everyone, you bet it'll be nice and smooth. Just connect all the dots. What would this do? It looks like this would come like this, right? It might loop over. It doesn't have to be perfect, but it should come down like this. There you go. By the way, this probably would kind of loop over like this. If you really wanted to know this design, it would probably come over like that. The only reason I know that is because I could tell the slope was really steep and it was getting close to 0 there. So it kind of fade in like that. It'd be more like, yeah. But remember, you're just doing a matching. You're just doing a matching. And then you continue. Cool.
Now because the tangent at like 0, 0, for instance, there is negative, is that why you put it down?
That's right. And you notice, you go, well, where should I put it? You're like, listen, I'd have to go in here and measure the little change in y or the change in x to that. We don't have to do that. We're just making a rough sketch.
But you could just put it like right below it.
Right below it. And that's good enough. Or you could have stuck it like way down here, you know, because you're just getting a sense of it. And if you're wondering, like, do you have to make a perfect sketch for me? I do matching. I think it's very fair. You know, it's the best way to go.
That's all we have to do for every graph.
Yeah, I'd give you like, the book did this too. I'd like the design. No, I do, I'd probably give you 4 graphs on the left, 4 graphs on the right. I'd be like, can you match these 4 with their derivatives? And once you did like a couple of these points, you'll figure out where it is. And we'll give you another one. All right. And that's what we'll do. We'll just do a bunch of these to the end. If you want to create one on your own, you can, we can, and we'll see what it looks like. We'll look for strange scenarios. All right. My next one. All right, how about just this then? How about this? Can you hear? Stop there. Just one up. Yeah, I mean, seriously, just something like maybe a parabola or something. But I didn't give you the equation of this, so I don't know if you knew, everyone. Maybe that's y equals x squared plus 1. Or maybe it's y equal to x to the 4th plus 1. So we're just going to make a rough sketch of what we think the graph's doing, right? In fact, I could even make this thing really kind of flatten out here. Don't worry, I'm just going to make it be more like, you know, right here, it just came down with. Then I was like, all right, hits the bottom, slope 0. Because graphs like y equal to x to the 4th, everyone, do stuff like that. Graphs like y equal to x to the 4th. They get really, really, really low slopes right there and there, but then it hits this bottom part. It's its lowest point there. All right, where's the slope 0? Everyone can see it. Do you agree? Right there. That f prime is 0. So where do I put the dot? Where does this go? I mean, does it go right here? No, it goes where? Right there. Someone agree? Because that's where slope is 0. This is where slope is positive. This is where slope is negative. True? So far, so good? Sure.
Because the bottom is kind of flat, it doesn't extend, does the...
Great question. There was one instant where it got totally a tangent slope would be 0. But then it just barely started increasing up this way.
So even though it's like...
Yeah, it just had a little lift and it kept going up. Like a very, very what? Not a very high slope at all. And just right after it hit that point right there, so I didn't want you to think it flattened out from like here to here. It was a straight line. It came down, back. Yeah, and just like a parabola, but then it did get some lift. But there was only one spot right there where it did it.
If you have like x to the 10th power,
Yeah.
what will happen?
X to the 5th?
No, x to the 10th power.
Oh, exactly. Yeah, and feel free to look at it in your calculator. It does that. Just kind of gets me in.
Would this be a single point?
Yeah, it'd be this 1 point. Yeah. You know where it is? At x equal to 0. X to the 10th, x to the 12th. You bet. Oh, and I got my dot right there. Now, what's going on over here? It's negative. Don't agree? You ain't have to mark it up, but I'm just going to go like this. Negative, and just come down here and go like that. Negative. How about right there? Positive. F prime positive. Right there. So what's this graph doing? Something like what? Maybe it's just a straight line, or maybe it's just a curve that has a little lift to it. Just a rough sketch, but isn't it doing something like this? It's kind of sloppy looking, but yeah, isn't it doing this? Yep, you bet. Now I want to point something out. What if this was y equal to x squared? Joe, would you try to do the derivative on that? What would be derivative of y equals x squared? Just so we can make connections here. Y prime would be a 2 in front, x, decrease the power by 1, right? And is that a straight line? Straight line, parabola. Does everyone see the connection here? See how but you could do this with any graph? Now what if this was, here we go. Let me do yours, really high power. What if this was x to the 4th maybe? Plus a, and look, it's shifted up, so plus a 1. What's that derivative? That would be a what? 4 in front, x, decrease it by 1 power, 4x to the 3rd. What's the derivative of that? 0. So and what's 4x cubed look like? What's a cubic graph look like? Yep. So it'd be more like, you know, but it'd still do this. That's what I mean when I kind of went sloppy here. I'm like, well, I'd have to have a little bit more knowledge about that graph. Good enough though, right? Just we're going to get a sense of how the derivative would look. Cool? All right, now this one's fun. Here, I'll make this thing. Another trig graph. Another trig graph. I like trig graphs. Anybody know what the graph sine of x looks like? Of course you do. Right? It's like a prerequisite skill. Can we just graph the sine of x curve? It goes like this. It goes like that. Right? Y equals sine of x. Hey, does anybody know what y equal to cosine looks like? I'll put it over here. What's cosine of x look like? I'm just going to put it over here. Y equals cosine of x. So let me go like this, and then it comes down like this. Known great's got the phase shift. Very good. Isn't that cosine of x? Okay. Cosine of 0 is 1. What's the sine of 0? 0. But I was wondering, everyone, can you get the derivative? Make a rough sketch of the derivative. All right, where's the slope 0? Boom! Right there, the slope is 0. What about here? Boom! Slope is 0. What's the slope in the middle? That slope right there. Positive or negative? By the way, I should say that if someone was sitting here the whole time going, I don't know how it's positive or negative. Yeah. Lines that go up from left to right, positive. Lines that go down from left to right, negative. I should say that. There could be someone here who goes, oh, I didn't know that. So that's a positive slope. So I just put it what, up in the air? Yeah. There we go. Over here, looks like it was what, negative? Over right there? Negative? All right. It's going to be smooth. And guess what, everyone? Guess what the derivative of sine of x is? Take a guess. You bet. And we're just going to make this connection. Guess what? If y is sine of x, guess what its derivative is? It's just something you can really kind of see it. If y equals sine of x, the derivative of y equals sine of x is cosine of x. And so now there's a whole section in the book for trig derivatives. So don't worry about trig derivatives yet. Sometimes we discover these things as we go along. They're like, we didn't prove it, but we're pretty sure. We can see, oh my gosh. You know, these trig functions, they both behave very similarly, but there's a phase shift going on. That's what's going on.
So y cosine of x is sine, y prime sine of x.
Ooh, I like this. If y equals cosine of x, he's investigating this now. See, I love when you do this stuff. You can play around with it. Well, what do you think it is? I'm curious.
Would be y prime sine of x.
Sine of x?
Yeah.
Play around with it. You're close.
Negative sine of x?
Who nailed that? Who was that? That guy just hit it. Hey, if you played with it enough, you would tell. You'd be like, oh, it's complete opposite. And you would have flipped. You know what makes a graph flip over? Just a what in front? The negative. I'm serious. Sometimes it's fun to investigate it. You're like, can I figure this out? And so if you play around with these graphs, you can see the derivative of cosine of x is actually a negative sine of x. Hey, don't worry. We'll give you. Remember my JVC thing for jumps vertical? I'll give you something that helps you remember sines and cosines. Okay. I'll just give you a little. When we get to that, and when that's after the next test, I'll just give you something like this. And you'll just go, derivatives go that way. The derivative of sine of x is, the derivative of y equal to cosine of x is, yeah, you can just write it down.
Oh, I understand.
Hey, here comes my next one. This one, everyone, I'm stealing from the textbook, but I changed it a little bit, so it's not the same one. But I thought it was very interesting. Is there anything that could trick you? I'm serious, you're like, there's no way you can be stumped on this. Yeah, but so let's look at something strange. Sometimes the strangest ones are the easy ones. Like a straight line. Now, does anybody know about straight lines and their slopes? They don't change. Well, if it was like this, the slope would be 0, right? But what do we know about the slope in terms of if it's a straight line like this or this? The slope remains the same. The slope is constant over the entire portion of that line, right? Forever and ever and ever. True? That's different than these parabolas and stuff. The slope changes. That's why you have the calc course, right? Change in slope. But if it's a straight line, the slope is always staying constant. True? So, let me just put a graph here. Here's the one I made up. It's not the same as the book. It's a little different. I just thought I'd do a... There you go. Let's say there's some function doing this. So this is strange. and when I don't see these nice smooth hills anymore. So how do you deal with this one weird case? Well, they're straight lines. And the slopes always stay the same, right? So how about, that's what we'll look for. And I don't see any hills, do you? So what I'm going to tell you right now, there's nowhere where the slope is 0. You go, isn't the slope there 0? Oh no, the slope does not what? The slope does not exist there. It's a corner. Everyone agree? So we'll talk about what we'll do with this. If the slope doesn't exist here, that's a corner. Does the slope exist there? No, so we'll figure out how we're going to represent that if it doesn't exist. A lot of you already know. But for this thing, everyone, all I know is the slope is constant. Just tell me, is right here, is the slope positive or negative? Negative. So if the slope's negative here, along this entire portion, okay, then I'll just do this. But I'm drawing a flat line. How do I know it's flat? Why do I know it's just somewhere it's negative, or why do I know it's going flat? That's right, it's constant. I'll give you, let's make up a number so people can see this. Sometimes it helps. And we'll make up a slope here. What's that slope? M is negative 2, right? What's the slope right there? M is negative 2. What's the slope right here? M is negative 2. It's not changing. It's always negative 2, right? The slope is always a negative 2. The slope is always negative 2 until it gets to this corner. Where do I got to put that corner? An open what? Open circle. Wait, the slope is always a negative 2.
No, I mean the open corner.
Oh, remember? Because derivatives do not exist at J's and V's and C's. It jump this kind of vertical tangent and at corners. So if it's not differentiable there, the derivative does not exist there, then I'm putting nothing there. Do you agree? Nothing. Does not exist. Hey, how about here? Yeah, you want to make up a number? What's the slope of this line? 1, you might say 1, slope 2, whatever. I'll just use slope 2. M is 2, M is 2, M is 2, slope is positive. So from here to here, I'm just going to do what? To there, and then what? How about for the rain part? Can you predict it? What does this, what's it do over here now? It goes back to what? There you go. That's the weird one. Everything else is basically the same. How about, I'm serious, I can't get too much crazy with these because all you got to do is follow the process, slope 0, all that stuff. I'm not trying to make a crazy one here. All right. Came up, and it came down. It came up, it came down. It came up, I just want to get it up a little bit. Get it up a little bit. Nice and smooth, isn't it? Just try to get a sense of that derivative. Same function doing that, right? It's periodic. That thing's periodic. I bet you its derivative is also what? Periodic, brilliant. Yeah, outstanding. Oh, and you can get a sense of just making that derivative. Now the question is, later in this course, are we ever going to go backwards? Yeah. Like, will we get enough prime? Go, can we get out? We'll just reverse this, that's all. Reverse the thinking, the whole logic. Look on this x-axis, you know where the slope's 0. That's all we'll do. That's all we'll do. Hey, I'm going to nail these spots right now. Where's the slope 0? I wanted to make that nice and smooth. Boosh. 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 Slope 0. One more. Should that axis go a little longer? Now, and I'm just going to do positive, negative, positive, negative, positive, negative, positive, negative, right? Slope right there, positive, negative. Positive, back. Back. Slope here, negative. Slope here, positive. Slope here, negative. And get back to 0. All right. Looks like another one of these trig derivatives. It looks like it's shifted a little bit, but that's all right. There we go. I think I try to brainstorm every funny case. I saw one that did this. Just try this one out. Try this dude. It wasn't in the textbook. I just saw this online. I was like, oh yeah, that's a good graph. Good graph, dude. What if it did something like this? Almost like anybody take statistics? A little bit similar to the bell curve. It just kind of went. That's steep and good. Just something like that. We can talk more about it. It looks like there's only one spot where the slope's 0. Do you all agree?
Yes.
But do you all agree that as it kept going like this, it looked like the slope was getting almost what?
0.
Yeah, it was getting very close to being a 0. And over here, it looked like the slope was leveling out and approaching the slope of what? 0. I'm going to use the word approaching it. I don't know if it really got flat, right? It looks like it kept going down there. Very close to what? 0. All right. So where's the slope 0? You see it? Right there? All right. Hit it. Hit it, everyone. Bap. Slope 0. That means right there. Got it. How about the slope right there? Positive. Positive. I'll get it like right there. That'll work. Positive. How about the slope right there? Negative. I like to put little tangents just so you see it. That's negative. That means it goes down here. But one last thing. Let's make a half-decent graph here. What about right there? I can see the slope is positive, but it's really what? It's positive, but it's close to what? Positive close to 0. Positive close to 0. How about right here? Right above 0, but positive. Do you agree? Yeah? Does that work for you? Like right there, I'm like, it's got a little slight positive slope to it, but it's almost 0, right? Like a road with a very, very low incline. And how about right here? Right there, that slope right there.
Slightly negative.
Yes! So how about like right here? So yeah. But that's like a bell-shaped curve, but this derivative would do something like this. And I'm just going to kind of let it line right there. It looks like it was getting really close, but we need more of that curve to see what it did. And by the way, it'd probably just keep doing that. Just keep approaching 0. Like that. Cool? That's it. I've hit every type of scenario you could think of. You all those, crush the test. Rest of the class is review. I'm going to join the lead. If anyone else wants to leave, you can. Beat traffic and stuff. But stick around if you have any questions for me. I'll be glad to do it with you. I got nowhere to go.
You want me to keep the tape rolling?
No, you can cut it off.
Fair enough.
Bye, everyone.